The following research constitutes representative high-resolution simulations of the dispersed flow film boiling regime, which persists during reflood transients in pressurized water reactors. I am Nadish Saini, and this work was the central focus of my PhD thesis performed at North Carolina State University under the supervision of Professor Igor Bolotnov. Nuclear reactors are designed to withstand several accident scenarios. Among them, the most challenging accident to analyze and model is the loss of coolant accident, wherein the reactor core gets depressurized and loses all of its coolant due to a piping failure, also referred to as a blowdown. Once a blowdown is detected, emergency pump systems reflood the core. Analysis of the thermohydraulic response of the core during the reflood phase is extremely important from a safety margin characterization standpoint. Prior experimental observations have established dispersed flow film boiling as the primary flow regime that persists in the reactor core during the reflood phase. Spacer grids and mixing vane structures play an especially critical role in the thermohydraulic response of the DFFP regime, primarily due to turbulence enhancement and the collision of dispersed droplets with these structures. Sharp increase in the heat transfer coefficient has been reported in the immediate downstream vicinity of spacer grids, which can be correlated with the increase in the interfacial area of droplets owing to their collision with the spacer grid assembly. The advent of supercomputing systems has now enabled high-resolution simulations of the DFFP regime, providing key insights into the flow physics in the vicinity of spacer grids and mixed vane structures, in addition to providing extensive supplement to the experimental data necessary for reactor design. For instance, the simulations enable us to capture the evolution of Sauter mean diameter of droplets at the downstream location of spacer grids, which in turn strongly correlates to the recorded heat transfer enhancements. Here, the Sauter mean diameter is reported for different upstream collision Weber numbers of droplets and found to agree well with prior experimental correlations. The high-resolution data collected from the simulations also enables insight into key downstream turbulence flow features. The Reynolds stress map is reconstructed here for the single-phase case, showing quantitative enhancement of turbulent mixing in the wake of spacer grid structures. A similar map is also reconstructed from the simulation data for the droplet-laden cases, which sheds a quantitative light onto the immense additional feedback to turbulent mixing observed in the wake due to the presence of droplets. To conclude, this research demonstrates the potential of high-resolution simulations to provide insight into the physics of reactor flow regimes, which are otherwise too challenging or prohibitively expensive to be studied by experiments. We have archived the data from the simulations, and it is intended to serve as a mine for the development of data-driven models for PWR thermohydraulic analysis. For further information on this research, please follow the references enumerated on this slide. Thank you for your attention.